Okay, all right. So we're gonna pick up here for our, I guess, technically first water-oriented lecture. And we're picking up right with osmotic pressure, right? So hopefully everyone remembers that osmotic pressure occurs when solutes are dissolved in water. Um, and why we care about this from a biochemical standpoint is that ultimately the concentration of the solute in a water dictates how much osmotic pressure there is in a certain solution, right? So admit. Um, so where this comes into perspective for again our class is that if there's a difference in the concentration of solutes across a selectively permeable barrier, we can basically see changes in the way water will move between those different solutions, right? So in our little cartoon here, we have an image or side A versus side B. Side B contains more solutes, so this selectively permeable membrane allows water to move towards the portion of the solution that has a higher concentration of solutes until the concentration is equal across that barrier, so it's equal on both sides. Any questions about that so far? Hopefully review. Okay, right. And so where this comes into perspective again for us as biochemists or cell and molecular biologists is that because this is the way water moves and water follows solutes, that can drastically impact, the tiny, tiny things that make us up and make us into what we are, right? Cells. So there's a few different types of ways we talk about how concentrated a solution is. So we've excuse me, uh, isotonic, right? So this is when the concentration of solutes is equal outside of a cell and inside of a cell, right? So isotonic, there's no net water movement there. So as water moves into the cell, water is also moving out of the cell. So there's basically just an equilibrium that's reached over time. Whereas a hypertonic solution, where the concentration of solutes is higher outside of the cell than inside it, there's a net movement of water outside the cell, which can cause a cell, if it's flexible enough, to shrink, right? So water will come out and that cell is going to shrink until the concentration within the cell is equal to outside the cell. And then lastly, hypotonic, where the concentration of solutes inside the cell is greater than outside the cell. So there's a net movement of water into a cell, which essentially, if the cell has no way to mitigate that increase in water flowing into it, this can be bad basically because cells can explode, right? So some cells are built to handle this, where they basically just continually pump water out of the cell, allowing it to not increase largely in volume. But not every cell is equipped with that kind of protein machinery. So it can be not good for certain cell types, or not good for saltwater organisms placed back into fresh water, because saltwater organisms handle water a little differently than us. Okay. So on the bottom here, just because we're short on time because of the hiccup here, I have still a little example of an experiment, if you want to call it that you can do at home. So you can actually take an egg, a non-cooked egg, and actually dissolve the hard shell out from around it. And then if you place that dissolved egg, it's still going to have a water selectively permeable membrane around it. If you place that into different solutions, you can actually, on a larger scale, visualize what occurs to cells when the same thing occurs to them, right? So if that egg is placed into a hypertonic solution, again, where the concentration of solutes is larger outside of the cell or the egg, there'll be a net flow of water out of the egg, causing it to shrink, right? If you do isotonic, the egg will essentially retain its original shape because there's no net movement of water in or out. And then hypotonic, where the concentration of solutes is greater inside the cell than out of it, water will actually flow into the cell, or the egg, causing it to expand. Right, so a little easier to see than cells, and hopefully everyone has had an opportunity to do this somewhere along the line here. We used to do an onion root, hypotonic, isotonic. activity in Gen Bio Labs. Not sure if they're still doing that or if maybe you guys didn't get the chance to do that. And so, right, relating this back to neurons, neuronal membranes, or even motor cells or muscle cells. Cells, in order for cells to do their jobs properly, they very, very tightly regulate the concentration of different solutes inside and outside of themselves, right? So specifically for neurons, neurons very tightly regulate the concentration of sodium outside the cell as well as potassium inside the cell, because in order for neurons to generate an action potential and communicate over long distances, they basically exploit that differential concentrations of solutes to generate an action potential, which we could talk about more if someone has a question about it, I suppose. But right, so neurons need to control the concentration of solutes inside and outside themselves, and so do muscle cells as well. That being, different solutes. But does anyone have any questions about that for now? Okay. Right, so basically just some comments to bring up about water and review, right? So the few slides we just talked about now, and then as well as the slides I posted last Thursday. Basically just reiterating that, remember, the intramolecular structure, properties of a molecule will dictate what intermolecular forces those molecules experience. And this is going to be important when we start to talk about weak acids, which are essentially weak electrolytes in solution. Remember, hydrogen bonding allows certain molecules to have extra strong intermolecular forces. Polar solutes dissolve polar solutes, or excuse me, polar solvents dissolve polar solutes. We didn't talk too much about it this year, but water has a very, very high specific heat, which allows it to take much longer to cool and take much longer to heat up. It's one of the key properties that allows life on Earth to exist the way it does. Water is also a critical co-reactant in many reactions. Again, we won't get too much into that. And then the structure of water and the polarity of water also drives key structural interactions in molecules, proteins, and substrate interactions, right? That'll come up again once we start talking about primary, secondary, tertiary structure in proteins. And we had a slide in the previous slide deck from last week about how water can impact how ligands interact with enzymes. So before we go into the next stuff, does anyone have any questions about basic stuff about water? Okay. All right. So we just mentioned this, right? So polar solvents dissolve polar solutes, things like strong electrolytes such as sodium chloride or magnesium chloride, where our ionic substance is going to completely dissolve, right? So we have a unidirectional area representing that where sodium chloride are going to completely dissolve. The same is true for strong acids and strong bases, right? If we throw a strong acid like hydrochloric acid, excuse me, or a strong base like sodium hydroxide into water, those are going to completely dissociate. Hopefully everyone remembers that about strong acids, bases, and electrolytes. And we've loosely mentioned up to this point, I can just say it again, right? That weak electrolytes or weak acids don't completely dissociate. They're governed by Le Chatelier's principle, and essentially the stuff around them is going to influence how much they do or don't dissociate, right? So this works better.
Can I get a face pixie stick with extra syrup? No, thank you.
Someone is not on mute and they're ordering pancakes, just as a heads up. I think it's this one. Can I mute this? Yep, there we go. Okay, cool. All right. Right. So if I
That's part of the video.
Oh, Mackenzie Burton. I'm also gonna mute.
Why don't
Okay. It's kind of like broken my train of thought, but so if you guys weren't aware, I guess this is how I'm going to roll into this, right? If you guys weren't aware, water ionizes spontaneously to a very, very small extent, right? So water can essentially, in an incomplete fashion, dissociate into our hydronium ion, H3O plus, and hydroxide, right? Just OH minus. So with respect to this, basically water undergoes incomplete dissociation. It can function as an acid base as well as a conjugate acid and a conjugate base, right? This happens spontaneously and it happens to a very, 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 very low extent. Does anyone know by chance what the KEQ or the KEQ of water dissociating spontaneously is? I don't think chance. Okay. So you guys have technically heard about this before, I promise. There's a reason the pH scale looks the way it does. Okay. So I'll spare all the walkthrough for all this, right? But so in order to calculate the KEQ for the spontaneous dissociation of water, we would set up our chemical equation the same way as anything else, right? We have our reactants, water, our products, H plus and OH minus. We can do the concentration of H plus times OH minus over water. And if we include a little bit of extra information, well, yeah, if you guys hadn't thought about it either, the molar concentration of water in water is 55.3 moles per liter. So in 1 liter of water, there are 55.3 moles. So that's going to be our denominator. And then in order to calculate our H plus and OH minus, we have to use a little bit of experimental evidence. So we can determine this using there it is. Using electrical conductivity measurements, we can determine that KEQ, or KW in this case, is equal to 1.8 times 10 to the negative 16th. So that means if we plug in all of our information, right, 55 times our value here, rearrange our formula, we essentially arrive at KW equals 1 times 10 to the negative 14th moles per liter squared. Does anyone want to take a guess as to why that negative 14 is important? How about this one? Does anyone know what pH plus POH always has to equal?
14.
14. Yeah, so that 14 actually originates from this calculation here, the derivation of KW equaling 1 times 10 to the negative 14th. Oh boy. Looks like we have a new student. Okay, so you're going to see some practice problems about this in the next set of homeworks, and it's really just a portion of using water and water chemistry. So we know that KW equals the concentration of hydronium ions, or H pluses, times the concentration of hydroxide ions. And we know that those two times each other always equals 1 times 10 to the negative 14th. Right? So basically, if we keep breaking this down, we essentially arrive at the concentration of H plus, which is always equal to the concentration of OH minus, right, when water is spontaneously dissociating, because we essentially have H2O splitting up into H and OH. We know that the H and the OH have to have the same concentration. We know that any given moment, unless you change something, the concentration of these two is 1 times 10 to the negative 7th, right? It's basically just the square root of 10 to the negative 14th. So at equilibrium and at 25 degrees Celsius, we know that the concentration of H plus is always going to be this, and the concentration of OH minus is also always going to be that. I'm going to mute somebody, I think. Naomi's my guess. Okay. right? So essentially a practice problem. I'm just gonna throw it up here and walk through it instead of pausing and letting you guys work through it. So how you could see this in a problem is you'd be given this information, right? So I could ask you what the concentration of H plus is in a solution of 0.1 molar sodium hydroxide, right? So again, remember, we know Kw, which equals 1 times 10 to the negative 14th, always equals H plus times OH minus. So if we rearrange this, we know what Kw equals, right? 1 times 10 to the negative 14th. We know what the concentration of OH minus is because sodium hydroxide is a strong base. When it dissociates, we know 0.1 moles of OH are going to be present, and this is a 1 liter solution. So we can essentially rearrange our formula so that H plus, the unknown, equals Kw, which is known, divided by the concentration of OH minus, which is also known, right? What that looks like is 10 to the negative 14th divided by 0.1, basically equals 10. Our numbers cancel out. And what we're left with is the concentration of H plus is equal to 10 to the negative 13th moles per liter. Does anyone know why that number shrank? As compared to 10 to the negative 7th? Or does anyone know that, or did anyone remember the name of the principle that may cause the concentration of products to shrink? Certain products, I suppose. Right, Le Chatelier's principle. So by adding 0.1 moles per liter of hydroxide to our solution, we're increasing the concentration of our products, and we're driving the reaction in the reverse direction. And again, also, we know that H plus times OH minus must always equals 10 to the negative 14th. So here are 2 more practice problems. If you want to try these at home or while you're reviewing this, pause the video now if you're watching this via the video. Otherwise, I'm going to just pause it if you want to pause it. Okay, hopefully you've unpaused it, right? So these 2 practice problems are going to use an OH concentration of 1 times or 1.3 times 10 to the negative 4th. So if we rearrange our formula again, we get OH equals Kw divided by H plus, plug in Kw, which is always the same, divided by our H plus concentration. I think I misspoke earlier. Here, our H plus concentration is 1.3 times 10 to the negative 4th. Set those up, divide each other, and now we know in a solution where the H plus concentration is 1.3 times 10 to the negative 4th, the concentration of OH minus is 7.7 times 10 to the negative 11th. Right, and then our next problem, H plus concentration is 4.3 times 10 to the negative 7th. Plug things in, equals, ultimately our OH concentration equals 2 times 10 to the negative 9th moles per liter. Okay, any questions about that? Basic, it's just a basic algebraic reorganization there. Okay, I already spoiled this one, right? So talking about the concentration of OH or OH or H plus in solution, saying 4.3 times 10 to the negative 7th can be cumbersome. So obviously there's a different scale system we use when we talk about the concentration of H pluses or OH minuses, pH and POH, right? And if you didn't know, pH actually originates from the phrase or term pondus hydrogeny, which means potential hydrogen, right? It's not just random. So we know in order to calculate pH, we just take the negative log base 10 of H plus, right? Which, if you're following log rules, can look like this: log of 1 over H plus, right? If log rules, if you just negate that, you can actually flip it. So, right, pH equals negative log H plus, POH just equals negative log OH minus. Another way you might see pH used when referring to the concentration of H plus is that H plus will equal 10 to the negative pH, right? And again, remember that 10 comes from the fact that this is a log base 10. So you may see it either way. Any questions about that so far? I hope not. Okay, right. So remember our KW equation, H plus times concentration of OH equals 10 to the negative 14th. This is what I've already basically given away. If we take the log of all those things, rearrange it, follow some log rules, we end up with, again, pH plus POH equals 14. And so up here in the top right, we have on top pH versus on bottom POH, and this is just meant to show, right, the higher the pH, the more basic a solution is, the lower the pH, the more acidic, and vice versa. The lower the POH, the more basic, versus the higher the POH, the more acidic, right? But they always add up to 14, right? So a pH of 7 corresponds to a POH of 7. A pH of 13 corresponds to a POH of 1. It's always, they always add up to 14, right? Even if, say, your pH is 0. If your pH is 0, your POH will be 14. And then this is in here because I've come across enough students that aren't familiar with what I refer to as the loop and swoop way to solve a logarithm. So, right, I call it loop and swoop because we loop and swoop. So in order to quickly solve log base 10 of 7, we can loop, right? So we take 10, the base of our log, raise it to the question mark as far as an exponent goes, and then we swoop and set that equal to 7. So 10 raised to the question mark equals 7. And so that it's going to be useful using log for some of the equations we have coming down the pipeline. And if you're wondering how to incorporate this with a negative log, right, because our pH scale is negative log base 10 concentration of H plus, we do it very similarly. We take 10 to the question mark, set it equal to 7, but it's going to be 10 to the negative question mark. So if there's a negative log here, you incorporate it into the exponent, the mystery exponent over here, and you set 10 negative question mark equals 7. Okay. Everyone okay with that? No questions? Okay, we'll keep moving along, right? So maybe you guys have seen this or not seen it, but been taught it and talked about it before, maybe in anatomy and physiology, right? We care about pH because ultimately the pH measurements of blood, urine, and other things can be useful for diagnosis, right? So hopefully you guys have seen this before, right? So basically, if your blood is too acidic, we call that acidosis, right? And this can happen in severe uncontrolled diabetes. It can happen if you have metabolic syndrome issues. Severe exercise can actually cause your blood to become more acidic. But if everything's working the way it's supposed to, that can be regulated and controlled. And then conversely, if your blood is too basic, that's referred to as alkalosis, right? So I think the easiest connection I make with this is if you were to eat way too many antacids like Tums, you can actually neutralize too much acid. Yeah, you could neutralize too much acid and actually make your blood more basic than it should be, which is also bad. And then over here, same thing. I include this every semester just to give you guys kind of a reference of where common household things are on the pH scale. So right here, right around neutral, right, human blood and tears, usually they hover around 7.4. Milk and saliva is a little more acidic. Black coffee has a pH of about 5. Beer, red wine, somewhere around 4. And then cola or soda, has a pH of roughly 3, similar with vinegar. And then we keep going down, right? Lemon juice, gastric juice, more and more acidic. If we go up, all right, so a solution of baking soda, so sodium bicarb is actually a little basic, around pH of 9. Household ammonia has a pH of roughly around 12. And then bleach, which is sodium hypochlorite, actually has a pH somewhere around 13. So any questions about that? Okay. All right. So I've defined weak acids and weak bases before. We talk about equilibrium constants, but I'll just reemphasize here, right? So when we talk about weak acids, usually we have our acid. After it dissociates, we have our conjugate base, and as well as an H plus. And so the key here is to be able to identify what is protonated and what's been deprotonated, right? So acetic acid's a fairly common weak acid used in problems. But ammonium down here, right, NH4 plus, can also actually act like an acid, right? So in the right solution, NH4 plus can dissociate into H plus, as well as its conjugate base NH3. Right. So one of the tricks to discussing weak acids is being able to identify what is the acid form versus the conjugate base. Okay. And so when we talk about these guys, right, we know these are weak electrolytes or weak acids, weak bases. So they're not going to dissociate completely. So we have to be able to calculate and discuss the KEQ of these substances, right? So we would set these up just like any other KEQ. In the case of acetic acid, H plus times CH3CEO minus divided by the undissociated acetic acid. And so these values more or less fall under textbook values, again, at 25 degrees Celsius and room temperature. So the KEQ of acetic acid is, under these conditions, always 1.74 times 10 to the negative fifth, right? Much smaller than 1. So the reaction here favors the products as opposed to the reactants. And so something else you should get used to if you haven't seen it before, but I think I mentioned it last week. When we discuss weak acids, we often just refer to them as HA and H plus and A minus. In which case, if you wanted to write the equilibrium constant of that generic weak acid, you just do KQ equals H plus times A minus divided by HA. And so when we discuss KEQs for acids, we typically refer to them as KAs because we're actually interested in, their potential as an acid. Yeah, okay, so that's how you calculate Ka. That's what Ka is. Does anyone know how else we refer to the strength of acids or the strength of acidic functional groups? Hopefully everyone's seen this in OChem. It's actually we also refer to the strength of acids as using the term pKa, right, which is just the negative log of Ka. And that's important because it's going to be used in the Henderson-Hasselbalch equation. Okay. Right, so just a note here, I suppose. So even though these are all weak acids, the stronger the weak acid is, the more likely it is to lose its hydrogen ion to solution, right? So of the two here, acetic acid is the stronger weak acid by almost, I think this is 100,000-fold in strength, right? More so than ammonium. And so how likely that weak acid is to give up its hydrogen and be content as an ion in solution, like the acetate ion, all that's, again, driven by the intermolecular structure of the acids. So the more stable a conjugate base is, typically the stronger it is as a weak acid. Okay, any questions so far? Okay. So, yeah, I bet the next question you're asking yourself is, what about weak acids with more than one acidic proton? There's a lot of these, right? So up here we have several examples. The first being carbonic acid. So carbonic acid actually has 2 acidic protons, right? H2CO3. So it can dissociate into HCO3 minus plus H plus first, and then HCO3 minus can further dissociate into CO3 minus, CO3 2 minus with another hydrogen, right? We'll just go down here to phosphoric acid. So phosphoric acid, which is actually a common acid used in laboratories to buffer the pH of solutions, has 3 acidic protons. So H3PO4 can dissociate into H2PO4, H2PO4 can dissociate into HPO4, and HPO4 can dissociate into PO4, right? And why this matters is because each one of those acidic protons has its own unique pKa, right? So the first, being the most acidic, has a pKa of 2.14. The second, the middlest of acidity of the 3, has a pKa of 6.86. And then the least acidic has a pKa of 12.4, right? Which is actually fairly weak, I guess is where we'll leave it from there. And why this matters and why we're bringing it up again is because whether or not this acidic proton dissociates basically all boils back down to Le Chatelier's principle, right? So the pH of the surrounding solution, otherwise known, right, as the concentration of H pluses in the solution around these guys, will actually impact whether or not your reaction proceeds forward or backward. So can anyone guess what would happen if we placed H3PO4 in a very, very basic solution? This one's, I suppose, worth working through with feedback from you guys. Does anyone want to take a guess if what would happen in terms of H3PO4 dissociating if we threw it into a very, very basic solution?
It would dissociate more.
Yeah, exactly. Do you know why? So what about its surroundings are going to help it dissociate a lot?
The fact that it's basic and it's trying to reach equilibrium.
Um, yes. So you're basically you're like 3/4 of the way right. So what do we know about a basic solution though, in terms of what our acid dissociates into? Is the concentration of H pluses very, very high or very, very low in a very basic solution?
Pretty low.
Pretty low, right? So if the concentration of one of the products is very, very low, we know based on Le Chatelier's principle that our reactant is going to dissociate more, right? So the extent to which these weak acids dissociate or reassociate is completely dependent on basically how much product there is laying around. That's going to matter for buffers when we get there. Like Chelsea. Okay, so this is meant to just be like a super quick exercise about identifying acid-base pairs, right? So I'll just quickly click this. So, which of the following is not an acid-base pair? So we know HNO2 and NO2 minus. Basically, that molecule's just lost its H plus. CH3NH3 plus, which is we essentially have an ammonia or a quaternary a quaternary amine here, carrying an extra proton. In the right conditions, aka the right pH solution, that extra proton can dissociate out, and you can be left with CH3NH2. So the middle choice here, which of the following is not an acid-base pair, is the correct answer here, right? So we know, I just used on the previous slide, we know H2CO3 can eventually dissociate into CO3 2-, but H2CO3 has to dissociate first into HCO3, right? So carbonic acid has to first dissociate into the bicarbonate ion, and then that bicarbonate ion can actually donate another proton to solution under the right conditions. So these are just here. I won't be asking any questions about percent ionization, but if you see this somewhere, like on the MCAT, right, percent ionization just equals the ionized acid concentration at equilibrium divided by the initial concentration of the acid. And right, this is just setting up our next slide. So we have all these formulas and all these different ways to discuss and calculate the concentration of H plus. Ultimately, what we want to know and we want to be able to use this stuff for is determining the concentration of an unknown weak acid in solution, right? Essentially, what's the pH going to be if we throw a certain amount of certain amount of weak acid into solution? And then how do we observe the behaviors of those acids in the solution? So hopefully everyone remembers titration curves from Gen Chem and Gen Chem 2. So this is meant to be a stereotypical titration of a weak acid. We have our OH added equivalents down here. So basically, right, this x-axis is just saying that for each of these ticks, more and more OH has been added to solution. On the y-axis here, we have our pH. So if we follow the pH as we add more and more sodium, more and more hydroxide ions, we can see that initially the pH increases very, very quickly, and then it slows. And then at some point later on, it also increases very, very quickly. And I'm ruining my question for later in the presentation, but that region where it flattens out and the pH increases more slowly over time is referred to as the buffering region for that weak acid, right? What's occurring here is the balance of protonated weak acid versus unprotonated weak acid is actually slowing the change in pH as more and more OH is added, right? And so somewhere in the titration of each weak acid, there'll be an inflection point where your curve flips from concavity to convexity. At that inflection point, we have a few different ways to refer to that as, right? So at the inflection point, the concentration of our undissociated acid is equal to the concentration of our conjugate base or dissociated acid, right? So they're equal. The pH at which that occurs, these two being equal, is actually equal to the pKa of that weak acid as well, right? So remember that pKa value, that's meant to represent the relative strength of a weak acid. The pH at where that inflection point occurs is also the pKa. And right, so if we go down here to this last way to refer to it, we call that 50% titrated because, again, essentially, we're halfway through titrating all the weak acid and neutralizing all the weak acid. Okay, and I guess if we look at this mathematically, so we have acetic acid that's still protonated, dissociating into its conjugate base and H pluses. If we incorporate our values from Kw and set up our equilibrium constant, that's going to equal H plus times the concentration of acetate ion over acetic acid. And again, that's always going to equal at 25 degrees Celsius, room temperature, it's always going to equal 1.74 times 10 to the negative fifth. But if you take negative log of that value, you'll get 4.76. And then so depending on where you're reading it and discussing it, you might call this referred to as the midpoint or the equivalence point, right? So equivalence point, again, is just referring to the fact that the concentration of acetic acid is equal to the concentration of acetate ion. If you see referred to as midpoint, it's called the midpoint because it's halfway through the full titration of that weak acid. So two different names that basically mean the same thing. Anyone have any questions so far? Okay, so right, we've been discussing weak acids. I'm lumping them all in together because one of the things that remains the same or consistent across all weak acids is that that behavior when you titrate them. So here we have, again, acetic acid. We have one of the acidic protons for phosphoric acid, and then we also have the titration of ammonium, right? So you can see each of these acids has that rapid increase in pH and then a slow, and then also another rapid increase in pH, but it all occurs for each weak acid at a different location along the pH curve. So for acetic acid, it happens at 4.76. For H2PO4, it occurs at 6.86, right? Again, if you draw a line right over here, you get pH 6.86. And then ammonium, it occurs way up high at 9.25. Right? It's, I say way up high, but it's not really that high. So at a pH of 9.25, the concentration of ammonium is equal to the concentration of ammonia. Excuse me. And so each of these different weak acids has its own unique buffering region, right? Ammonia is going to buffer well between a pH of 10.25 and a pH of 8.25. This version of our phosphoric acid is going to buffer happily between 7.86 and 5.86. And again, acetic acid will buffer happily between 5.76 and 3.76. So again, where that flattens out is due to the strength of our weak acid. And a reminder, right? The stronger a weak acid is, the more readily it gives up their proton to solution because its conjugate base is more stable. And this is the question I basically answered earlier, right? So each weak acid and its conjugate base pair have a unique range where they buffer the change in pH along their titration curve. So again, one of the reasons we care about this as biochemists or cell and molecular biologists is that if we're studying a certain reaction or maybe studying a certain metabolic pathway that occurs best at a certain pH, right? Say we're trying to study reactions that occur within our cells that are typically at 7.4 pH, right? Of these three buffers, we would likely choose H2PO4 to be used to set up our buffer because HPO4 will happily buffer, again, basically one full pH below its pKa, 5.86, and one pH above its pKa at 7.86. So 7.4 is within that region, and phosphoric acid is going to more readily and more strongly buffer that solution there, as opposed to acetate or ammonium, barring what biological impacts ammonium has on a cell or metabolic pathway and acetate. Okay, any questions? Okay, so this is all basically just a review of everything I just discussed. We talked about the Henderson-Hasselbalch equation last week. On the next, I'm going to end on the next slide, but on the next slide and subsequent slides on Thursday, we're going to start to use the Henderson-Hasselbalch equation. So just as a reminder, right, the Henderson-Hasselbalch equation is pH equals pKa plus the log of the concentration of A minus over the concentration of HA, right? So we'll end right here on this review slide. Okay, so if anyone has any questions, feel free to stick around and ask. Again, sorry about the confusion with class. It's my fault, like I said, because it was blind copied. I didn't see that it only went to me and not everyone else. So otherwise, if no one has any questions, I guess I'll see you guys on Thursday.
Thank you.
Thank you.
Sorry.
You're good.
Thank you.